everyone. Welcome to the Data Services Office Hour. I'm Michelle DiPalma, and I'm here with Daniel Parks. How are you?
Hi, I'm doing okay. Michelle, and you? Everything okay?
I'm good. So talk to me about, I know we're going to talk about Metro DR, but I don't know what part, and I don't have the overview. So can you tell me what we're going to go through today?
Yeah, the idea is to continue a little bit with what we have been covering, with all of the offerings that we have regarding OpenShift and DR. And with Annette in previous episodes, we have gone a little bit through regional DR and just briefly spoke about Metro DR. So the idea today, and maybe in 2 or even 3 episodes, depending on what we have time to cover, we can go into depth about the Metro DR solution, when to use it, when not, and the architecture, so all of the tiny bits that form Metro DR.
Nice. Do we get a demo with this one too?
I'm going to go through today. The idea is that we're going to cover the external Ceph configuration. So we are going to go through the terminal and we can check what it looks like and how it gets deployed and all of the details from a terminal. So we're going to, in the end, we're going to have a full demo of Metro DR as well.
Awesome. Okay, let's get started.
Yeah, so I'm going to share my screen just to share some slides that I have. Just a moment. I think that I'm going to share just...
Okay, there we go. Nice.
Yeah, so just to give a little bit of context to people that are maybe watching this for the first time regarding disaster recovery and what Red Hat has to offer currently, I'm going to just very briefly go through the options, and then we would also cover a little bit and speak about a little bit about Metro DR. So regarding the Red Hat offering, we have like 3 different types of storage now that we of storage and backups. Let's say that it would be the cold DR. That this is really OEDP, so it's backups and recovery, or backup and restore, that we have done all of our lives now. So it's really having granular backups for OpenShift applications. We have already covered this topic in the show in the past with OEDP. Even last week, we covered a little bit the new features that we have in OEDP 1.1 with the data mover. So the thing with the cold disaster recovery solution is that the RTO and the RPO are quite high. By RTO and RPO, I mean the time that it takes since the application goes down to have it back up and running again, and also the amount of data that you may lose when a disaster happens. So if, for example, we are taking backups, let's say in the morning, we have a disaster in the afternoon, that range of time since we took the backup until the disaster happens, all of that data is going to be lost. So that's really speaking about RPO, and as you can imagine, with this kind of solution is quite high. Then we have what we have like warm DR, that is the regional disaster recovery that we covered with Annette quite in depth. In this case, it's a synchronous replication, so we can have geographical separate clusters, and the data is being replicated when on a set interval between both of our OCP and ODF internal clusters. In this case, the RPO is much less. It's just in the interval that we have set. So if, for example, we set a replication interval of 5 minutes, the loss of data that we are going to suffer during a failure is going to be in that 5-minute range. And the RTO, that is really the time for the application to be ready, depends on ACM, because we have already spoken about this, and we will also mention it a little bit later, that all of these solutions, or the regional DR and Metro DR, use ACM for triggering the failover of the application. So when we want to failover our application because there has been an issue in that site, in that host, whatever, we can trigger the failover and failback using ACM. So the RTO, in this case, that is the time for the application to be ready, is what ACM takes to stop the application in one side and start it on the other, or making sure that everything stopped on one side and starting on the other side. So that would be regional disaster recovery. And then what we are going to cover today, a little bit more in detail, that is metropolitan disaster recovery, or MDR, or Metro DR that we normally call it. And this is, we mentioned hot DR because this is synchronous replication. What we mean by synchronous is that each write that the application does is going to be replicated to the other side. So really synchronously, so that really there's not going to be any loss of data. So the RPO is going to be 0 or very close to 0 because the data is synchronous. And then you're making sure that each write is always stored in both sides before you get the acknowledgement back to the client. So in that sense, RPO 0 and the RTO, the time for the application to be ready, again, is managed by ACM. So it will be, again, in the range of 1 to 2 minutes, 2 minutes and a half, depending on what it takes to move the application from one side to the other.
So question, so for Metro DR, Ceph is always external?
Yes, like that's a very...
The defining feature of Metro DR. Okay, just checking. As opposed to regional DR, just for anyone listening, where it's internal.
Yeah, that's a very good point. And let's move into that. So with regional DR that we have the image here, you can work with OCP and ODF internal deployments, meaning that you don't need an external Ceph cluster. That is exactly what we're going to cover in detail today. That's a requirement for the Metro DR. With regional DR, you have two sites. You have ACM running on a third site, and then you're replicating between both of your ODF internal clusters. So no need for external Ceph in this use case. But when we move into Metro DR that we have in this slide, we do have the requirement of an external Ceph, because really what we are doing to achieve synchronous replication and also being able to lower the RPO now to 0 is stretching the storage. So the Ceph cluster, the external Ceph cluster, is really getting stretched between both of the sites. And what we're going to cover in big detail or in very taking a close look to is what you just mentioned, the Ceph external storage. Because in the end, we have to think that when we work with ODF, let's say that the brains or the storage layer that is managing everything behind ODF is actually Ceph, and that's what we're going to explain today a little bit in detail. And going into this, before we go into the actual stretched deployment, I wanted to just briefly cover this topic. I don't know if you get this question now and then also, Michelle, where there's some confusion around the internal mode and the external mode that I was just mentioning before.
Right. Okay.
So just to very quickly to make this clear, when we speak about ODF deploying it in internal mode, is because we are deploying Ceph inside our OCP clusters. So we have our OCP clusters with worker nodes, and the actual Ceph deployment is going to happen inside our OCP cluster, inside our workers. So that's thanks to the Rook operator that is part of ODF, and Rook takes care of deploying all of the Ceph services for us without us even noticing. It's completely transparent, and it also manages all the life cycle of the application of Ceph, all of the upgrades, everything like that is managed by Rook. So it makes our life really easier. With internal mode and having the OCP cluster and the ODF storage on the same nodes, we are also unifying storage and compute. So we can grow storage and compute together as needed. The other thing that we have to take into account is with internal mode, because Rook is doing a lot of things for us, is really a very opinionated design or a very opinionated deployment. So ODF is going to deploy Ceph in a certain way, and we are not going to be able to tinker or to tune a lot of things because we want it deployed in one standard way, so it's easy to maintain and upgrade, and Rook takes care of it.
Okay.
The big difference that we have there now is with external mode, we have our OCP cluster with our worker nodes, and then we have the Ceph cluster deployed on RHEL, on our standard operating system. We have RHEL, and then we deploy Ceph on top of that operating system. Once we have Ceph, go ahead.
I was just going to ask, so in external mode, will you be showing us is ODF still involved? Like how do you actually communicate with the external cluster? How is that managed, et cetera, et cetera? I've never done external mode, so this is new for me.
Yeah, that's a good question. And we're also, I don't know if we're going to have time today, but or in next episode, we're going to show how to connect an ODF cluster in external mode to Ceph. But to answer your question, ODF, you still need ODF. So you are going to go into your OCP cluster, you're going to deploy the ODF operator. But when you get the UI for the ODF operator, you're going to select for your storage system, you're going to select external Ceph. And then you're just going to provide it, let's say, with the IPs and the authentication needed to connect to the cluster. And then what is going to happen is that Rook, instead of going ahead and deploying a full Ceph cluster on OCP, is just going to deploy the CSI provisioner and drivers, so the worker nodes are able to provision and mount RVD volumes, FFS volumes, depending on what you need. So you only get like the drivers in OCP and ODF to connect to the external Ceph.
Okay, that makes sense. Okay, thank you.
And one thing, another big difference, let's say, or another thing that is really nice about the external Ceph or external ODF deployment is that you can connect one or more OCP clusters. So you could also have 4, 5, 6, whatever number of OCP clusters, and all of them can be connected to a single beefy, let's say, big Red Hat Ceph storage cluster that you have deployed. So this can be a really nice feature to have all your storage on a centralized point. And on the other hand, touching again on scale and performance, when you have an external Ceph cluster, because the life cycle is being managed by Ceph, so it's an external team, an external Ceph team, a storage team that is managing the life cycle, you can also do a lot of performance tuning. You can tinker with a lot of options, a lot of configurations that are available in Ceph. And in the same way, it's really a scalable solution where you can have many nodes available to have a really big raw size in your storage available to consume.
Nice. Oh, so question, and you may get into this later. So from the inside of ACM, are the failover options are they similar to regional? Like you have to name who's primary, who's going to be backup, and you can have them going this way, but it's one-to-one as opposed to like one-to-many. Is all of that the same, even though we're external?
Yeah, that's a good question, and we're also going to see it on the next episode where today we're going to center on Ceph and the external Ceph deployment, but on the next episode that we're going to go and speak about the failover and failback of the applications using ACM, we're going to see that is very similar to the experience that you get when you deploy or you use regional DR. You have the application, and the only thing that you're going to select if it's going to be synchronous because you want to use Metro DR, or if it's going to be asynchronous because you're using regional DR. But the UI and how you configure DR for the applications is exactly the same experience.
Okay. Awesome.
This is just to mention what we have just said, that you can have one or more OCP clusters connected to a single RHCS cluster. The recommendation for the external cluster is to be bare metal, but there can be exceptions where we also support VMware or any VM deployment of Ceph. And very quickly, just to mention this slide is that with Red Hat OpenShift Platform Plus, when we have that subscription, we already have mentioned that we get Odf Essentials. This means that we get what we have on the left of the slides, that we get like the basic functionalities from ODF, like being able to use read-write once, so block, read-write many. We can also use snapshots, cluster-wide encryption, and we also have object storage. So we have all of the basics covered. But then we have the advanced edition with OpenShift Platform Plus, where we get the external mode, where this is where we use or we connect to a Red Hat Ceph storage, where we can connect one or many OCP clusters, and we also get the DR bits, like Metro DR and Regional DR. So just bringing this up so we we know no, there are two different options when we are getting the Red Hat OpenShift Platform Plus subscription to be able to use for DR.
Okay.
Let me just also stop sharing a second because I'm going to show a new tab with you very quickly.
Okay.
Just let me know if this is okay in size to see it.
Yeah, I think that's okay. Yeah.
Perfect. So what I wanted to cover with these slides or with these diagrams, I just drawn these diagrams this morning to try and explain a little bit the differences between single Ceph and also the differences between the stretch Ceph cluster, no? And they're in black and white, so they're not that they don't have color, but I think that you can't fail. No? If you're in black and white, there's always easy to follow in any case, and you don't get distracted by the colors. So this is a standard Ceph deployment where we have a single site. As you can see here, we just have one site, and we have a single subnet. So this means that all of our Ceph nodes are connected using a level 2 connectivity. So there's no routing going on, although there could be. We could use L2 or L3 TCP/IP connectivity between our Ceph nodes. In the demo and what we're going to use and see today, all of our Ceph nodes are communicating under the same subnet. And then we have here our Ceph cluster, and we have 6 Ceph nodes configured. I'm going to start with this single deployment, and then we will move into the stretched cluster, so we can see the differences between both of them. But I'm just thinking that if we have time, I'm just going to show a moment a very basic introduction to 2 or 3 important concepts of Ceph, just so it's clear for us when I speak about monitors and managers and Osds, just so it's clear what each of these services do and what is the function inside Ceph. So
part of what Rook takes care of, right? Like
yeah,
this is under the hood. Okay.
yes, takes care of all of this under the hood. No, so let me just share again a moment because I think that it's better if we cover this and then we're going to understand it better.
Okay.
So going into the basic architecture or the components that form the Ceph architecture, we have like an underlying layer, called RAIDOS, that is really a distributed object layer. It's software-based, is reliable, elastic, and it takes care of the replication and erasure coding for our Ceph cluster. So really, RAIDOS is taking care of the endurance of the data and also the reliability. So it's also taking care of when we want to increase the size of our cluster. If we want to add nodes, we want to add new drives, then RAIDOS will take care of that. So it's done transparently and it won't affect the higher level. So there's quite a lot of intelligence inside RAIDOS. And one of its first or its most important features is really keeping consistency. So it's going to ensure that there's not going to be any data loss, even if we lose a drive, if we lose a host. So it's taking care of data placement, of recovery. All of these things are happening inside RAIDOS, this distributed object layer. So there's so many functions and so much goodness inside RAIDOS that it takes, so it makes the life of the clients or the services that are running on top of RAIDOS easier. And by this, I mean that, for example, the ones that we have here in gray, like RAIDOS Gateway, RBD, they don't have to worry about the resilience of the data. They just have to do what they're meant to do well, but they don't have to worry about all the underlying things that RAIDOS is abstracting for them. So going into the services or the clients that consume RAIDOS, we have the RAIDOS Gateway service, that this is an S3 endpoint for object storage. So going into ODF, for example, when we deploy ODF on premises, we get a storage class coming from Raiders Gateway that is going to make object storage possible. No? So we have an S3 endpoint, and we can do puts, gets, and we're going to be able to use S3. This comes from this service, not from Raiders Gateway. There's also RBD, that is virtual block device. So this translated into ODF is when we want to get a persistent volume claim for our application that is read-write once, that is using block. We're going to use the RBD storage class, and really we are consuming the RBD service available in Ceph. And finally, we have CephFS, that is a distributed network file system, and here is the same thing. No? In ODF, when we want to be able to mount the same file system from several pods using read-write-many, we are really using the CephFS service available. There are other services in Ceph, but these are the ones that we actually currently use with ODF. So as you can see, we have the Rados layer with all the intelligence, taking care of all the details about resiliency of our data, and then a higher level clients or services that offer us different types of object, block, shared file system, and also object storage. Going into the Rados layer, and we are only going to explain 3 of the services that are going to help us understand when we go through the stretched configuration. We are going to speak about OSDs, monitors, and the manager. With OSDs, there's like kind of a one-to-one relationship with the actual disk, that we are consuming or using to save our data. And with monitors, there are like the guardians, that keep quorum and keep the state of the cluster. So just a little bit more detail on each of these. So for OSDs, as you can imagine, there's almost a kind of a one-to-one relationship between an OSD and a drive, and is where we store the data. It can be a hard drive, it can be flash media, but in the end, it's where we are storing our data. And they're also in charge of servicing the client I/O requests. So when a client wants to read or wants to write an object, a file, he's going to speak with the OSDs. The OSDs can go from having a very small number, maybe 1, 3 just in a proof of concept or just doing a test, to tens of thousands in a production cluster. So they can scale to a huge number in a single cluster. Why they can scale to such big numbers, or one of the reasons that they can scale to such big numbers, is because these OSDs are actually intelligent. So they're not just a passive thing just doing IOPS. They're actually intelligent in the sense that they're able to peer and communicate with the rest of the OSDs that we have in the cluster, and they are going to speak between themselves, and they will say, okay, I see that this OSD hasn't responded in certain time. I'm going to tell the monitors that this OSD is down. They're also taking care of replication and recovery. So for example, if we have a failure on an OSD, on a drive, we replace that drive with a new one. The OSDs by themselves are going to speak between each of them, and I'm going to say, okay, this new OSD has a very old version or doesn't even have a version of this object. We need to replicate it, or we need to recover that object on this new OSD. And all of those operations will be done between or by the OSDs by themselves. So by being intelligent, they're really removing a lot of burden from the monitors or from a centralized metadata controller or something like that, like you would have in legacy storage appliances. And this allows us to scale to a very high number. With monitors, again, they're the central authority for authentication, data placement, and policy. And really what they do is they protect the cluster state through quorum. So they're using the Paxos algorithm, and you always need to have quorum to access to read, write data from the cluster. So they are taking care that the state of the cluster is consistent of all of the components, services that are running on the cluster. They have a centralized view, and they make sure that everybody in the cluster has that same view. That is really important. One thing to notice is that monitors do not serve data, or they do not even serve metadata from the files. No, they are just serving maps that have an understanding of the location of where each thing is in the cluster, but they are not in any case in the data path of our reads and writes of the client. So, and then
Okay,
we have, yeah,
oh, wait,
go ahead.
so go ahead. I was going to say, you go ahead and finish with manager, and then I wanted to talk about if we went
Perfect.
into what we would see. So, okay, so what's the role of the manager?
Yeah, the manager, just very quickly, it aggregates real-time metrics we have here, but really it takes a lot of information from all of the different components that we have in Ceph and then aggregates them in a centralized place. It also runs the dashboard, so we have a new nice UI dashboard on Ceph where you can do configuration. You can also check aggregates, throughput, information about the health of the cluster. All of that is running on the manager. And it also hosts pluggable modules. So there are modules written in Python mainly that you can enable or disable and will extend the features available inside Ceph, by using those modules that are enabled or disabled in the manager. So go ahead, Michelle.
Okay, so my question is, regardless if we're talking about ODF and Rook, or we're talking about external, if we were to do a deep dive on one node inside of an internal or external Ceph cluster, we would see an OSD per disk, right? Where you said there's a one-to-one relationship. So we might see a ton of OSDs running. And then the monitors, though, you don't need as many, but you would have quorum. Let's say you have 5 or 7 or whatever you've decided, depending on, those would be sprinkled about the infra node. So you may or may not see a monitor running there, depending on where things were placed. And then above that, the manager would run, you said there's a one active, one passive. So you would see only two managers running, one would be active, and that could be wherever you decide to be. So in the case of Rook, it decides all of that for you. But for external, you have to make those decisions yourself. Like you actually do the placement of where you want all this stuff to be. Okay.
Yeah, that's a very good point, and you explained it very well. But yes, that's exactly the case. No, for Rook, all of those decisions will be taken care for you. You don't have to worry. Rook also uses like the placement labels that you have, placements, or let's say topology labels that each node has. So it knows, for example, that it has to place a monitor on each of the racks or each of the availability zones, for example, in AWS. All of that intelligence goes into Rook and it does all of that for you. But when we're working with external Ceph, as you just mentioned, we have to configure that placement. No? So we have to decide where each service, where we want to place each service, we could say.
Okay.
Perfect. So that was the introduction and that I wanted to share just before I started speaking about what you mentioned about placement, about how everything is set in the cluster. So last time, let me share again the diagram that I had here.
Sure. Okay.
So as we already explained, one side, this is the standard configuration. And then I wanted to go on what you were just speaking about. So for example, we covered monitors, a very important service that we have in Ceph. And as you can see, in our deployment, or in this example, we have 6 nodes and we only have 3 monitors. As you just mentioned, because we need quorum, it's always going to be an odd number. Otherwise we will be into problems if we lose a node. So the idea here is that because we have 3 monitors, we can lose a monitor, we can lose a full node. And because we have more than 50% of monitors left, these two would agree on forming a quorum between both of them, and we could keep having IO or serving IO from this cluster without the clients noticing. So that's the first decision that we have to take, where we are going to place our monitors. In this case, in this example, I don't have racks, I just have hosts. So we are just going to place them arbitrarily in these 3 hosts. There are certain rules to how many services you can put together into a node, always trying to conserve or not, or let's say, be sure that one service is not going to overrun the other one, and then you're going to have issues with the stability of your cluster. No, so we would also share at the end where all of these rules are available. They're quite simple in any case. No, so those are the monitors. The managers, as you just mentioned, we have two managers, one active and one passive. If we lose one host, the manager that is running active is going to be failover to the next node, and it's going to keep serving the metrics, and also the dashboard is going to be available for us. No? So that's the manager working in active passive. And then we have Rados Gateway. Rados Gateway, we mentioned it before, that is our S3 endpoint. And with Rados Gateway is really an HTTP RESTful API, meaning that being HTTP, what we can have is a load balancer on top of Rados Gateway. So in case we have a failure of one of these nodes, all of the client requests would be redirected to the other node, and we will keep serving client requests for object storage without any issues. No, so that's something to take into account. With Ceph 5, that is the one that we are using in this example, there's also an ingress service available by which you could get an HA proxy deployed with all of the automation, so everything is done for you. That would actually load balance these Rados Gateway services. But anyway, that's another topic, just mentioning, just in case someone is wondering, well, we have to take care of the load balancer to have HA. That's already available and automated for you with the ingress service in Ceph 5. And just finally, we have the Mds Services. These are for CephFS, because CephFS is a shared file system. File systems need a centralized place to store metadata. So the Mds daemons take care of the metadata for the shared file system. Again, here there are many different configurations that we could have. Active, 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 passive. We are using the simplest one, the one that you get by default, no, that is active, passive for these Mds deployments. Okay, so this is covering a little bit of the and we forgot about OSDs. We can't forget about OSDs. Right. That, as we said, OSDs are really the ones in charge of writing to our drives. You normally have a one-to-one relation, so you see one OSD, one drive. That's not always the case, so you can have exceptions where, for example, you have NVMe drives that have loads and loads of IOPS, and you could get some performance advantage by dividing that drive into two OSDs. So you will have two OSDs for one NVMe drive, and that could, in some cases, increase your performance. No, like, for example, when using small blocks, that could be beneficial. But in any case, in most of the deployments that we're going to see, we will have a one-to-one relation, or in any case, to make things simpler, not today. So here we have an OSD per node. This is just normal. In every host that you have disks, you're going to have OSDs, no? Because they're the ones in charge of serving reads and writes from those drives. Okay, so moving forward, when we have this cluster deployed, we are going to be able to offer to our clients these different services that we have already covered. No? So we're going to be able to offer block, shared file system, and also RGW as the S3 endpoint. Next step would be connecting an OCP cluster. And we already spoke about that a little bit with your question before, but here we would deploy the ODF operator into the OCP cluster. That will give us the ODF external UI where we can tell it, okay, connect to this cluster with these credentials and this IP. So it needs certain information, and then it would be able to connect. And this cluster would get the CSI drivers deployed and would start actually being able to mount to provision volumes from this cluster. It's important to note that on the OCP cluster, we only deploy drivers, so there's no actual data. Let's say that you go ahead and lose this full OCP cluster, all of the information will still be available on your Ceph cluster. So there's complete decoupling between data and compute in this scenario. That's not the same for ODF internal, no? So something to think about. Okay. And the other requirement that is a given, but just in case, is that we need to have connectivity from our OCP cluster to the ODF cluster. Again, it can be L2 or L3 TCP/IP connectivity, because let's say that the worker nodes need to speak with the monitor and with the OSDs to get the latest cluster map, and then with the OSDs to do actual reads and writes. So we need to have connectivity. And then, as we said, we could have one cluster or many OCP clusters connected to our external deployment. Okay, so going a little bit deeper, and we're getting close to the end, so please just keep here just for a moment when we cover the stretch deployment. No, so things to notice on this diagram. No, right away we can see that we have 3 sites. No, instead of having a single site, now we have 3 sites: data site 1, data site 2, and an arbiter tiebreaker site here. So, speaking about networking of our Ceph cluster, first we can say that in this example, we are using, again, we are extending the VLAN between our data centers. So really, we are simplifying the deployment, and we're using the same subnet in all of our sites. This is one way in which we can configure the communications between our sites, but it's also perfectly possible, and it works fine with Ceph, if we have routing between our sites. No, that would be a very common scenario where we have routes between our sites, and each site has a different subnet. Here, to make our life easier and just to show how this is configured and the demo, we're going to use the same subnets in all of the clusters. So while we're covering the networking side of things, let's go into latency. No, you can see here that data site 1 and data site 2 are the ones that are going to be doing synchronous replication. So they have a requirement of 10 milliseconds of round trip time between both of the data sites. So we can go up to that value. Going over that value is not supported and also not recommended, because when a client does a write, let's say that comes into this OSD, because we are using replication, that client is not going to get an acknowledgement until the data gets also stored on an OSD on the other side. So we have to add to the normal disk latency that we're going to get with Ceph, we have to add also crossing from one side to the other. So we need to add this latency, so it can affect our performance if we have too higher values between both of the data sites. This is a completely different topic with the arbiter or the quorum side, because it's not in the middle of the data path. No actual data from the clients is going to this site. So as you can see from this diagram, we can, or let's say that Red Hat has tested as high as 100 milliseconds, round trip time between the arbiter and both of the data sites. So this perfectly fits with latencies that you could get from any cloud provider. So just in case, if you don't actually have a third site where you can put your arbiter, you could perfectly deploy it on a cloud provider, and you will be okay with the latencies there. So that's something to take into account.
So I noticed something interesting. So on the third site, the arbiter site, you also have a monitor, right? So we have an odd number of monitors, but the stretch cluster has has the same amount, and then the deciding ones on the arbiter. That's interesting, because I was actually going to ask you what happens when because we have to have an odd number of monitors and so on. Okay, so yeah. Okay, interesting. That's the way.
Yeah, that's a very good point. So if you like, we can go into monitors, and as you can see, as you just said, before in the normal installation we had 3. You could also have 5 in the normal installation, but here it even makes more sense. And here we have 2 monitors on one side, 2 monitors on the other side, and then we have the deciding monitor on the tiebreaker side or the arbiter side. So just in case we lose connectivity to one of the sites, we are still going to be able to maintain quorum with the arbiter side and the other side that is still running. So that's why we can have quorum with these 3 monitors.
Okay.
You could say, okay, but if we had 3 monitors, this would still work perfectly, because with 3 monitors, if you lose one, you still have the arbiter and the other one. Why are we choosing or recommending to have 5? Because let's say that if we have a full data site failure, and we lose this data site, we could maybe lose it for weeks, and then we're only going to be running with one site and nothing else. So really, having a single monitor is having a single point of failure during the time that the second data site is down. So that's why we would recommend to have 5 monitors. So even though we have lost a site, we still have 2 monitors inside this data set running.
Okay.
And it's also important to notice that when we configure or when we finally enable the stretch mode, the OSDs are only going to be able, or they're only allowed to speak to the monitors that are on their side. So they can never cross over to the monitors on the other side. No, that's another thing to take into account.
Okay. Okay.
And,
so they can
if you take
back about, like you said, like the OSDs communicate, right? So we're just saying you're not communicating with the stretch piece, communicate on your side, and you report to your local monitor what's going on, but only about your side. Okay.
Yeah, because the monitor, as we mentioned, the monitor has the full view of the cluster. No, he knows everything. He knows the placement of where everything stands, or at least it has the maps to know where everything is. And then the OSD just has to contact the monitor to get that map, and that's enough. So really, there's no need for this OSD to be speaking to the monitors on the other side for the cluster to work. So in that sense, we are reducing the communication between both of them.
Okay.
Also, go ahead.
No, I was going to ask a question about the manager. So if you have another thought about the monitors, we should complete.
No. Go ahead with the managers.
So the monitors, the managers, active, passive. So then what is the role of the arbiter in the managers? None, or like
none. Yeah, none, because really, even if you see here different boxes, don't get confused, because this is a single Ceph cluster. So even it's a little bit misleading that I have 2 boxes here, but this is a single Ceph cluster. So the manager architecture is active, passive. That's fine. No, we have one active, we have one passive. If we lose a full site, then this is going to be active, and we're still having a high availability, because all of this is just the same Ceph cluster. So we can just fail it over.
Okay.
And it's a little bit the same with Raiders Gateway in this case. You can see here that we have RGW. We have one RGW instance. We could also have more, and it would be recommended to have more. We just don't have enough nodes here to do it. But you have different RGWs per site. If you have a full site failure, the other RGW service is going to keep allowing gets puts from all of the clients that have that RGW configured.
Right, we have a load balancer that would manage all of that automatically.
Yeah.
And okay. Interesting. Okay. Awesome. Wow.
Yeah. So getting close to the end, but adding another layer here. This is just to show that once we have everything deployed, we would have an stretched offering for the clients of block or share file system, and also Raiders Gateway S3. So if we deploy an OCP cluster in site 1 or site 2, all of them are going to share the same Ceph cluster that is now stretched between between the data sites.
Random question. Do you happen to know in external Ceph, like what if we, for whatever reason, only wanted replica 2? Can we configure that in external Ceph? Because I think that is a feature of ODF, right? Do we get to choose? Okay.
That's a very good question. You can't. So that's a really good question. That's why this was a little bit ugly, but I also added it here, so I didn't forget to bring this up. Okay. So when we enable the stretch mode, we need to have replica 4. So that's the minimum. And I will explain it why we actually need replica 4. So we have different Ceph pools. Pools is just a logical aggregation or a logical way to store different objects or to divide different objects depending on the functionality that we want to give it. So for example, we have a pool that is the RBD pool. Okay, that's where we're going to save all of our block images, all of our block volumes. Now we have RGW, so it's just a division on how we logically separate objects. With that in mind, each pool can have a different replication factor. No, we could have replica 2, as you mentioned, replica 3, or in the case of when we are enabling a stretch cluster, replica 4. So when you deploy a standard Ceph cluster and you're moving it into a stretch, automatically Ceph is going to transform all of the pools that you have with replica 3 into replica 4, and it's going to do that for you because that's a must, no, for this to work, no. So that's something that you are going to get automatically done once you enable the stretch mode.
And what's the motivation that, like, once you lose a site and you're just left with one site, you at least have, even if you don't have 4, you could have 2? Like, so is it replica 4 across the whole stretch, meaning like 2 over, or is it even within a site you're going to get 4? I'm just trying to figure out, like, if I were mapping this out for my own external Ceph cluster, how does that impact? How many replicas do I get on one side of the stretch that I have to worry about, and so on? So, because that's going to determine where I place stuff.
That's a great question. That's great, and that's the reasoning is what you just mentioned. No, so when we have replica 4, we're going to get we're going to show all of this. I'm sure we went over time today, but I will show it on the next show. We're going to see the placement rule where we actually specify, okay, put 2 replicas here, 2 replicas on the other side. We're going to see all of the details on the terminal, but just the theory is what you just mentioned. So we are going to configure a rule for each of these pools, and we're going to tell it, you have replica 4, and you have to store 2 replicas on one side and 2 replicas on the other side. So then we are sure that if disaster happens, we lose site 2, we know that in site 1, we have 2 available replicas. Again, we need 2 because we don't know the amount of time that data site 2 is going to be down. It could be months, it could be a week, it could be a day, no, but you don't know. So you really need to have 2 replicas available to be sure that you're not going to lose data and that you can tolerate a further failure in this site. Because let's say that if you were only with replica 1 and you got a failed disk, then you will lose your data. No? So that's why we are requiring replica 2, and you would store 2 replicas on site 1 and 2 other replicas on site 2 to tolerate a full site failure.
Okay, another question. So after what you said, it says replica 4, and then you have min size 2 and min size 1. What do you mean by min size there?
Yeah, so the min size is, again, it's a configuration per pool, and it's the minimum size that you need to have available to be able to write to the volumes or to the pools, no, that you are using. So another thing that happens is that when you are working in a stretch mode, but you don't have any failures, I'm also going to show this in the next day, the configuration is replica 4 min size 2, meaning that you need at least 2 replicas for IO to continue. The thing is that if we lose a full site and we go into what we call a stretch mode, that's done for us automatically, this changes for our pools, and then we have replica 4 and min size 1, meaning that because we have lost a full site, we only have 1 site, and then we have 2 replicas, we still want to be able to do writes. So we are reducing the min size from 2 to 1, so we can still keep allowing writes while we have a full site down.
Okay, great.
And just a thing before I forget is also that because when we lose a site, we are only going to be working for a time with 2 replicas. Another requirement that we have is that we use flash drives, in this case, SSDs, NVMEs. It's just because of the endurance and also the higher IOPS that they offer, that they can ensure that the recovery time, if we have a failure while we only have 1 site, the recovery time is going to be much faster than just a normal spinning drive where the number of IOPS per drive is very low, no, compared to an SSD. So that's another requirement to take into account when designing this kind of metro-DR solution.
Wow, amazing. Okay.
And going into the final slide that we have is just adding the final bits, no, that we were missing. That is couldn't be that way. Adding OCP. So what we have here is that we have added an OCP cluster with ODF external, and we connect it to our stretch cluster. Even if I have a line here, this is connecting to the single stretch cluster that we have. And the same for the OCP that we have on data side 2. It is connected to the stretch cluster. So both of these ACM managed clusters that have OCP and also the DR operators deployed are able to consume storage from this stretch cluster. And then we have the hub that we can deploy it on the arbiter side or on another side. It's not a requirement, but here with this 3-side kind of architecture, it fits very well to place your hub, your OCP ACM hub inside the arbiter side. No, so as we mentioned before, ACM, and we're going to see this in detail on the next episode, ACM is taking care of the failover and failback of the application. So it needs to be on an external, on a different site that is not actually on the data side, because it has to have the view of both of the clusters. So if we have a failure, let's say on site 1, what is going to happen is that ACM is going to say, okay, we need to fail over to site 2. Let's do a fencing of all of the IO in this cluster. We need to be sure that nobody is writing to the volumes, because in this case, we are sharing the same volume. So we have to avoid at all costs that we have 2 writers to the same read-write once volume. Otherwise, we could have corruption. No? So we fence all of the IO, and then ACM says, okay, we are sure that everything is fenced. Now we're going to do the failover, and it moves all of the applications into this site. It starts consuming the volumes that it had in the other place, because they're the same volumes. That's why the RPO is 0. And then you could start using your application on site 2. No, that's a little bit the high level of how it will work.
Awesome. So hopefully we'll get a demo of really the hub, right? Looking at ACM, watching it fail over, and then it'll be interesting to talk about where it's important, I think, for Metro DR to understand where the decisions happen, right? So if a site goes down, your external stretch makes the decision over here anymore, we're going to the other side, and then the monitors on the arbiter site know, and then ACM can make a decision about failing things over and where things go. But it's not that decision, because it's external, right? It's happening in the Ceph cluster and RHCS, as opposed to, let's say, in ODF, the way it would if you were doing regional PR. Okay, that was awesome. Now I understand.
Right. So the idea. The idea is that we went over time completely, because I wanted to show you a little bit of the terminal today, so it wasn't everything in slides, but we went completely over time. So the idea could be in the next episode, go directly into the terminal, showing the 3 or 4 concepts that we learned on the diagram today about Ceph and Ceph, actually seeing it on the real flesh, on our servers, and how it is deployed and how we configure placement. And after that, we are ready to go, as you mentioned, with ACM and all of the DR parts that move the failover, the applications from one side to the other.
So this is Metro DR part 1 overview. Part 2 is when we get into the weeds and start messing around and seeing how it's configured and maybe do some failover stuff. So anyway, I want to thank you. That was fantastic. Everyone look forward to part 2 and where we go, we set it up and then we break it. Of course, that's what we like to do in storage here. So anyway, have a wonderful day. Thank you so much again. I have much deeper understanding of external Ceph, and I'm really looking forward to the demo. It's going to be great.
Thank you.
Thanks.
Bye, Michelle.
See you in the next episode. Okay, bye.